Hello everyone, I'm Matthew Barania, and today my topic will be on polyesters. So, start off, we know that the average amount of plastic waste that we as a planet produce is around 300 million tons each year, and that number is continuing to rise. And we also know that the world produces more than 300 million tons of plastic each year. So what does that mean? That means that 80 million tons are being recycled or being used in a different way, but 300 million of that is still going to waste. So that brings us to a question like, what solutions are there? What can we do about it? And there are many things that we could do, right? We can reduce the amount of plastic that you use, and honestly, like one main way is to just not use plastic, right? Plastic water bottles. I know like that's something that everyone uses. I use it sometimes, but it's like we need to cut that out of our life if we want to reduce the amount of plastic that we're using. We can use your own reusable bags when buying groceries instead of buying the plastic bags that obviously every grocery store gives you. You can cook your own food to avoid getting takeout, to avoid plastic cutleries, or even styrofoam. And finally, recycle, which brings us to my topic for today, which is polyester from recycling. So, some background information of polyesters, or some background information before we start, are that organic compounds are defined as anything that contains carbon, with the exception of carbon monoxide, carbon dioxide, and hydrogen cyanide. Hydrocarbons are compounds consisting of only carbon and hydrogen. Every single thing on Earth is made up of atoms. Atoms made up of protons, electrons, and neutrons. On the outside of every atom are the electrons, which are negative, and chemical bonds are the force of attraction keeping atoms together in a compound of a molecule. This is review from last year. Now, something new is that polymers are large, usually chain-like molecules that are built from small molecules, and those small molecules are monomers. So, for example, we have ethene monomers. Through polymerization, create polyethylene, as you see in this photo. But today we won't be focusing on esters. We're not going to be focusing on polymers. We're going to be focusing more on esters. But before we go on to polyesters, we need to go through the two things that make up polyesters, which are carboxylic acids and alcohol. So, carboxylic acids. A carboxylic acid is characterized by the presence of a carbonyl, which is C with double bond to an O, and a hydroxyl group on the same carbon in the terminal position. The arrangement of the atoms is called a carboxyl group, and this is the general formula, which is the parent attached to carbon, which is double bond to a oxygen, and a single bond to a hydroxide, right? So in this example, we have propanoic acid, right? You see the carbon chain is 1, 2, 3, making that propane, and again it's connected, a double bond connected to a oxygen, and a single bond connected to a hydroxide, making this propanoic acid. For alcohols, so an alcohol is basically any class of organic compound with one or more hydroxyl group attached to a carbon atom of an alkyl group. So the general molecular structure of alcohol is a parent attached to a alcohol, right? Or a hydroxide. And again, R is any hydrocarbon, so this can be propane, butane, pentane, right? So example here, pentanol, right? The parent is 1, 2, 3, 4, 5, pentane, right? And then the terminal is attached to hydroxide. So this brings us to esters. So an ester is a neutralized carboxylic acid characterized by the COOH group. And the H, however, has been replaced by an alkyl group. What does that mean? Right, so you see our general equation, our general formula. You have R, which is the parent, right? Again, to a carbon, double bond to the oxygen, single bond to the O. And usually a carboxylic acid would be OH, but this H is being replaced by another parent chain. right? Which comes from the alcohol. Again, how our esters are formed, right? How are esters formed? So esters are formed through a process called esterification. So esterification is neutralization of a carboxylic acid with an alcohol to yield an ester in water, right? And as you see here, right, we have the carboxylic acid, right? The parent chain doesn't really matter at this point. But as you can see, the carboxylic acid. So what happens? How does it become an ester in H2O, right? As you can see, the H, the hydrogen from the OH from the carboxylic acid gets, I guess it connects to the OH from the alcohol, right? And that creates the byproduct of water. And the parent, the R prime here, connects to the O, which becomes the second parent of the ester. So here's an example of esterification. And here we have pentanoic acid. You can see 1, 2, 3, 4, 5 carbon chain long. Pentanoic acid and butanol, 1, 2, 3, 4 from butane, right? And that creates this ester and the byproduct of water. And you can see what I explained earlier just happened, right? This OH from the butanol bonds with the H from pentanoic acid, creating the byproduct of water, and the parent of the butanol attaches to the O, and here you can see 1, 2, 3, 4, right, from the butane, 1, 2, 3, 4 of butane, right, and this is 1, 2, 3, 4, 5 from the pentanoic acid. So the question now is, how do we name this ester? And this brings us to ester nomenclature. So to name this ester, right, the first part of the name, which is R prime, is taken from the alcohol, right? So for example, we have pentanol, right? We take the base name of pentanol, which is just pentane, I guess the alkane version of pentanol, which is just pentane, right? And we make that into an alkyl group, and that becomes pentyl. So that'd be our first part of the name. Next one, second part of the name is taken from the carboxylic acid, but you would take out the oic acid and change it to OH. And the third step is basically the same as like any other nomenclature. Other functional side groups or chains must be numbered, named like usual, like mono, di, tri. Loci numbers are also important if you have any branches. So here's an example of the esterification again. So how do we name this? So our first step is to take the alcohol, right? The first part of the name is the alcohol, right? But an alkyl group of it. So butanol, which is just butane, really, becomes butyl. So butyl is our first part. And pentanoic acid, we take out the oic acid and it becomes OH. So our final answer is a butyl pentanoate. So here's a quiz. Which ester would form if ethanoic acid and propanol were to neutralize? So give me the name and the structure. So I'll give you a few minutes. Just pause the video if you need to. So to answer this question, so what do we first need to do? We need to first find our products, or sorry, our reactants, or not find it, but just like make a structure of them, right? So ethanoic acid, right, as you see here, has this structure. Propanol has this structure. So what would that become? Well, we know that byproduct of water. So we take the OH from here, we take the H from here, and we know that it would become like this, right? So the ethanoic acid, right, is still on the left side, it's the R, and the propanol, right, becomes R prime here with the byproduct of water. Okay. So how do we name this? Again, we take propanol, which is propane, which as an alkyl group would be propyl. So the first part of the name, propyl, and ethanoic acid becomes ethanoate. So with our final answer being propyl ethanoate. This brings us to our next lesson, Unit 2, Atomic Structures. So connection. So back to the process of the creation of polyesters. We know that during the process of creation, to create the alcohol, it requires a pretty high temperature. Like in the website, it said around like 150 to 210 degrees, which is pretty high in itself. But then after, when creating the ester by combining the alcohol from the previous reaction, which is the monomer alcohol, with a carboxylic acid, this temperature is risen to 280 degrees. So question now is, why do the melting points of these differ? And this can be answered through two ways. So first, intermolecular forces. And if you remember, last year we went through the three types of intermolecular forces, dipole forces, hydrogen bonding, London dispersion forces. And I'll go over them like pretty briefly today, right? So dipole forces, you should know, have a positive and negative pole. And as you see in this photo, right, chlorine has a negative pole, hydrogen has a positive pole. Opposites attract because of the law of attraction, right? And they connect to each other. They attract to each other. This means, again, opposite poles attract in the formation of a weak dipole-dipole bond. Hydrogen bonding. So hydrogen bonding, as we know, is the strongest bond out of the three intermolecular forces, and it's basically a strong dipole-dipole force that occurs with hydrogen when hydrogen is bonded to either oxygen, nitrogen, or fluorine. As you see here, oxygen to hydrogen. So this right here is it's a hydrogen bond. And this brings us to the final intermolecular force, which is London dispersion forces, right? An intermolecular force between two nonpolar molecules. So basically, again, if you remember from last year, it's a temporary attractive force that results when the electrons in two adjacent atoms occupy positions that make the atoms form temporary dipoles. So this right here, these are temporary. This is when electrons moved to one side of the atom momentarily, for a moment. And at that moment, there's a bond that's created, and that's what London dispersions are. As we know, every single molecule has London dispersion forces. And again, London dispersion forces are the weakest intermolecular force. So now the question is, how do they affect melting and boiling point? So, main idea, right? The stronger the intermolecular force, the more energy required in the form of heat to break them apart. Therefore, the higher the melting and boiling point, the stronger the intermolecular forces. So the question is why? Why does that happen? Why is the stronger intermolecular force creates a higher melting and boiling point? Well, if you think about it, right? More bonds, actually not more bonds, the stronger the bonds, the more energy it would take to break those bonds apart. Right? For example, hydrogen bonding. If in hydrogen bonding, it's so much more difficult to break apart than, let's say, a London dispersion force or a dipole-dipole force, like a regular one, right? Which means that if we were to compare two molecules in this case, right, we have methane, in this case we have methanol, right? Again, they have the same carbon chain, the same parent, which is just methane, right? One carbon, except methanol has an alcohol, methanol is an alcohol, meaning it has a hydroxide, and hydroxide is hydrogen bonding. And because of that, right, we see that we notice that methanol has a higher melting and boiling point than methane because it has the hydrogen bond, meaning that it has a stronger intermolecular force, meaning it requires more energy to break apart. Now, the next factor in the difference of melting and boiling points is carbon chain length. So similar to why different intermolecular forces cause a change in melting and boiling point, the longer the carbon chain, the more London dispersion forces it will have, resulting in a higher melting and boiling point. So in this case, we have methane, ethane, and propane. They're all alkanes, but as you can see, if you think about it, right, the more the carbon chain, the longer the carbon chain, really, the more bonds it will have, because more carbon chains, meaning, we can just imply, like we assume, more London dispersion forces, more forces. Even though the forces aren't stronger, there's more of them, and that leads to more bonds needing to be broken, right? Meaning more energy needed to break those bonds, resulting in a higher melting and boiling point. Now, as we see here, these are all just single bonds, but what would these bonds look like? And they differ depending on if it's a single bond, a double bond, or a triple bond. And that's when we go into sigma and pi bonds. So sigma and pi bonds, basically just different shapes of bonds depending on if it's a single, double, or triple bond. So a sigma bond is the lobes of each pair point towards each other and directly overlap. I'll show an example very soon. And pi bonds are orbitals and multiple bonds are parallel to each other and overlap. So basically, the formation of pi bonds are due to the existence of double and triple bonds. So you see here, pi bonds, as you can see, right? They're more of like a figure eight shape, right? And where it gets connected to, right? And it's actually on both sides, so a figure eight shape here and here, right? And where the connection is between the lobes. Remember in here, the ends of it, right? And they're parallel to each other, and this is the pi bond right here. Used right here, the pi bond. And the sigma bond would be overlapping each other. As if you can't really tell, but there's an electron in there. But the sigma bond, they overlap each other, kind of making like a Venn diagram type shape. So, just some like information to know. A single bond has one sigma bond. A double bond has one sigma bond and one pi bond, and a triple bond has one sigma bond and two pi bonds. So, question, consolidation. Given these two molecules, which of the following would have the higher melting and boiling point, and why? I'll give you just a few seconds. So just pause the video and unpause when you're ready. So, what do we do? All right, so which one would have the higher melting and boiling point and why? And this is the answer. So on the left molecule is the alcohol. Right molecule is an ester, right? So the alcohol would actually have the higher melting and boiling point than the ester, because if you notice, the alcohol has all three types of intermolecular forces as opposed to the ester. So alcohol has hydrogen bonding, has dipole-dipole, and London dispersion forces all in one. That in itself, actually mainly just because of hydrogen bonding, it has the stronger intermolecular forces, meaning that it requires more energy to break apart, leading it to it having a higher melting and boiling point. So given this Vesper diagram for this molecule, what type of bond are each bond in terms of sigma and pi? I'll give you another minute. So I hoped you spend some time to solve this problem. This is a really easy question because we know that single bonds have one sigma bond, right? And a triple bond has two pi bonds and one sigma bond. So this is what it looked like. Given the Vesper diagram for this molecule, what type of bonds are each bond, right? So this is a sigma bond because it's single bond. And there's two pi bonds here, and there's a sigma bond here, and a sigma bond here. Brings us to lesson 3, unit 4 of equilibrium. So, connection, as we know from the video, there is a neutralization reaction between carboxylic acids and alcohols, resulting in the formation of an ester, which is actually a salt because it's a neutralization reaction. So we can use this properties of both the acid and the base to find the properties of the ester, whether it is neutral, acidic, or basic. So to find the property of the ester, we need to understand what produces acidic, basic, and neutral ions. So for neutral ions can be produced in 4 different ways, right? So if it is associated from a strong base or a strong acid, the conjugate base and the conjugate acid would be neutral. If it is an alkali metal or an alkaline metal, for example, lithium, calcium, magnesium, etc., it will produce a neutral ion. Again, if it is a halogen, neutral ion. If it is a polyatomic anion that is mostly dissociated, for example, nitrate, phosphate, and sulfate, it is a neutral ion. So to create acidic ions, in general, if your conjugate acid is associated from a weak base, the conjugate acid will have the same properties as an acid, meaning that is acidic. So the general formula for acidic ions is weak base with water. This water could really just be a strong acid, right? Because this acts as an acid in this case. So a weak base with strong acid, right, makes a conjugate acid and OH. And this conjugate acid right here is going to be acidic, mainly because it's from the weak base, right? And yeah, to go on to basic ions. In general, again, if your conjugate base came from a weak acid, the conjugate base will have the same properties as a base, meaning that it's basic. Again, the general formula is almost very similar. So a weak acid, right, plus water or any strong bases would create H plus and a conjugate base, and this conjugate base is going to be basic. So we have an example here. We have acetic acid, right? So acetic acid is a weak acid, while NaOH, which is sodium hydroxide, is a strong base, right? So since we know this, how do we figure it out that if the pH is basic or if it's acidic? Well, we know, again, NaCH3OO, right, is a conjugate base with basic properties because it came from a acetic acid, which is a weak acid. Weak acid, if you know our formula, weak acid will result in an acidic conjugate acid. No, sorry. A weak acid will result in a strong basic conjugate base, right? And then H2O is neutral, you can see, because it came from a strong base, right? Strong base became weak, acid, right? So now we just have our net pH basically. So NaCH3O is basic while H2O is neutral, making this basic. So here's our quiz. What reactants would not create a neutral ion? Strong acid, alkali metal, halogen, and a weak base. So I'll give you a minute to figure it out. So let's go over these. Actually, the minute's passed, so if you pause the video. So let's go over each of these. Strong acid would create a neutral ion because a strong acid, again, will create, if you remember back to our lesson, will create a neutral ion. Alkali metal is near the edges of the, near the left edge of the periodic table, and it will create a neutral ion. Halogen, same thing, create a neutral ion. So the only thing we have out of the process of elimination is a weak base, and that is the answer. Why? Because if you remember, weak base with water will create a strong conjugate acid, and that right there isn't neutral. So in conclusion, we know now from the video that polyester is made from waste. In particular, it is made from plastic, right? However, this creation of polyester, right, can be bad for the environment if not made in a safe facility, as it releases toxic fumes into the air. So what can we learn from this, right? So we as a society can learn a lot from this, from just the creation of polyester clothing, right? We know, or what they did here is they created something reusable from waste. So instead of taking the plastic and just throwing it into the garbage, throwing it into landfills, polluting our oceans, polluting our environments, you know what I mean? Like, they used it to create something that we can use again. And we need to find stuff like that. We need to find ways, instead of wasting, wasting our waste, we can reuse our waste in a way that can benefit us again. In this case, clothing, because clothing is really beneficial to us. It, keeps us warm. Fashion, of course, but at the same time, we need to find ways to use polyester, or the creation of polyester, we need to find ways to use this waste in a way that does not affect the environment. Because even if you're doing something good, if something bad is happening in the process of doing that good, it's not good, right? So in this case, creation of polyester can be bad for the environment. Again, it releases toxic fumes if not contained properly, right? So find facilities to do it safely so that we don't cause any more harm for the environment. And we as society, as people, need to innovate. We need to create more things and just to find ways to reuse our wastes in an efficient and safe manner. And here are my citations. And thank you for listening to my presentation. I hope you learned something new. And bye.